The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Good afternoon, everybody. My name is Alizadeh, and I'm CEO co-founder of Giatec Scientific. We are a knowledge-based company spun out of University of Ottawa and Carleton University in Canada. And over the past 5 years, we've decided to develop different kinds of testing solutions for the construction industry, and in particular, concrete testing. So let me give you a brief background about what we do. At Giatec, we are focusing on different types of innovative and smart solutions, technologies for testing concrete. As I mentioned, we have 2 main categories that we're focusing. One is durability-based quality control of concrete. And these are lab devices for various applications, from permeability assessment to resistivity assessment. If you notice, what's common about these old devices, that they all use an LCD, a monochrome LCD, and that's the whole data communication that you have with the testing methods. And it's very archaic. Nowadays, with the advancements in mobile technologies, you can get much more powerful technology on a smartphone, better graphics, more accessibility, and more data communication. So with the second type of device that we developed, we focus on wireless communication between the measurement tool and the mobile app. So we started to develop mobile apps for corrosion detection and various types of activities, such as resistivity measurement. So essentially, we don't have any display on the unit, and everything is done and displayed on the mobile app. So, but the presentation is about on-site measurement of concrete properties, so I'll go into another application on what we're working on. So by the raise of hands, how many of you have searched online for concrete in Google Play or App Store? There's one. Okay, yeah. So if you search online for just keyword of concrete, you'll find thousands of apps. I mean, there's literally thousands of apps on the App Store and Google Play. Anything from concrete calculator, and I didn't know what is a concrete calculator until I downloaded one, and it's essentially a volume calculator. So any kid out of high school can do that, and then it estimates how many bags of concrete you need to put in that space. And there are also apps for, as you showed in the previous presentation, for design of elements, simplified design of concrete elements. And there are also apps for general knowledge, like basic civil engineering concepts and definitions, dictionaries, and things like that. So this shows that it's so simple to develop programs and applications and make them available to millions and millions of people worldwide. And so this is a tool that is available to leverage, and why not use it in the construction industry. So our focus has been essentially on bringing mobile-based technologies, and we refer to them as IoT solutions. IoT stands for Internet of Things. And that's a very common keyword in the IT sector. Essentially, you want to connect everything together into internet. So by smart homes, smart TVs, smart fridges that can tweet what they need, what you need to do in the shopping, so things like that. And we wanted to bring IoT applications to the construction sector. And the first focus was on compressive strengths. So this is what I'm going to focus in the presentation and show how we can leverage mobile technologies to monitor compressive strengths of concrete in situ. So as you're familiar, the process of concrete construction involves bringing concrete to the job site using a ready-mix producer's truck, pour concrete. Well, you take cylindrical specimens for general quality control, but you also have specimens that are cured in the field and are sent to the lab for field-cured specimen strength measurement. And that has a very practical application, which is essentially formwork removal, application of load on the structure, opening traffic on a highway or concrete pavement, repairs, turning off the heat when you're doing some element curing. So when you have that sort of specimens cured, you send them to the lab at 1 day, 2 days, 3 days, and then you wait for the results from the lab, and then you can make a decision on what you're going to do next. So that's the process, and it's delayed, as you know, and it's not that accurate because you have to send one sample. You can't have that many in-field cured specimens. So there are other non-destructive test methods, as you're familiar, such as pull-out test, the Schmidt hammer, and those are not adopted that well because of the high variability of the results. So the only most adopted technology that is out there for real-time concrete strength measurement is maturity. So maturity is standardized by ASTM, and it's been adopted by almost all the DOTs. It's part of the building code in Canada. It actually clearly states that you can either do the Breck test or you can do the maturity. So for maturity, you develop a calibration curve that essentially correlates between the temperature profile of concrete and the strengths of concrete at different days. And then use that pre-calibration curve, go on the field, monitor the temperature of the concrete in the field, and then you can estimate the strengths in real time. The way that people do it is that you have thermocouples, temperature sensors, wire temperature sensors essentially, that you put in the concrete, take the wire out, and then at any point in time you go plug in your data logger to the wire to collect information. And then you have to sort of analyze the data to see on the curve where you are and then estimate the strengths. So the process, as I said, is simple. Just place temperature sensors in the concrete, obtain data, which is essentially the temperature data. Then area underneath the temperature profile gives you the maturity index. And then from the calibration, you can see what is the strengths. There are two equations in the ASTM 1074 for maturity calculation. One is Nersal equation, one Arrhenius equation. There's a European standard for maturity, which is called weighted maturity, which is popular in Denmark, Netherlands, Scandinavian countries. So all in all, this gives us sort of an accurate measurement as a replacement of field-cured specimens to test. But the challenge is that, well, you have to install these wired temperature sensors in place, then get a data logger, a clunky piece of equipment, monochrome LCD, and then have the expertise to analyze the data. And believe it or not, you have to take care of the wires. And with a lot of job sites you go and they say, oh, where's the wire? They cut it, it's a safety hazard. So because of all that hassle, people still go back to the Breck test. And so although it's labor intensive, although it's delayed results, and also it's not accurate, they prefer to do the field cured specimens, and I can't blame them. These are actually pictures from real job sites in Canada. This is, on the left, there's a tunnel that they're using temperature sensors, and they had to put signs that says, do not cut wire. And so this is for the wired ones. And if you have a hobo box, the hobo boxes have to be connected to thermocouples at all times. And they also get damaged in the rain and get kicked at. And there was actually a case that the hobo box was stuck in the concrete. So they lost all the data. So we thought, why not develop a solution that could replace all this, that could change all this? And it hasn't been possible until recently to do something like that using mobile technologies. One of the reasons was that electronics was not there. Bluetooth technology wasn't strong enough, and it was consuming more power than before. So it was only until 2 years ago that we had low energy Bluetooth technology that was released to the market. And that enables us to run a sensor for a couple months on a coin battery. And on top of that, the signal is strong enough to go through concrete, which is not designed for, like Bluetooth technology is designed for open air communication. But nowadays, the technology is cheaper and stronger, so we can leverage those technologies and get that communication from something that is fully embedded in the concrete. So that's why I decided to develop wireless embedded sensors that are fully embedded in the concrete. So nothing is sticking out, everything is in the concrete, all the measurement is done there. And after that is simply a mobile app that you can use to communicate with a sensor. So everybody has a smartphone. You can have apps on Android and iOS platforms, and just walk up to the job site. There's nothing there that, again, you have to find and hook up your device to it. Connect the sensor wirelessly to the app and download the data. Very, very simple. So the way it works is that You essentially put the sensor in place. And again, these are Bluetooth technologies. There are wireless communication protocols that are much stronger than Bluetooth, so they can go through meters of concrete, like radio wave, but they're not practical for mobile-based applications. And the only communication that we have nowadays in mobile smartphones is Bluetooth, although we have like near-field communication, NFC, but that's very, very close-range communication. So the closest we can leverage using mobile apps is Bluetooth. So essentially, we have a Bluetooth transmitter here with a battery and memory and everything here. And then you have wires that go anywhere within the slab. So you can install the transmission near the surface to ensure that you have a strong signal coming out of concrete, and then put the wire within as much deep as you want. Like even mass concrete, you can go as deep as a couple of meters, 5, 10 meters, and then have all the storage and communication through the main part of the sensor. And then you pour concrete as usual. It's very straightforward after that. Nothing is in the way of the construction workers, so they don't complain. And then you walk up to the structure using your mobile phone. These are actually construction workers and technicians that took them only 3 minutes, 4 minutes to learn how to use the app. So especially the younger generation of engineers, apps are intuitive for them. They don't have to follow a user manual. They don't have to follow instructions. You open the app, you know where the menus are, you know how to communicate, and within few minutes, you can communicate with the sensor.
How far away?
So the Bluetooth communication gets weaker and weaker as you put the sensor deeper. So within like 2 inches, you can get up to 8 meters of connection range. But if the Bluetooth sensor is in the open air, you can have like 100, 150 meter of communication range. But 6, 8 meters is more than enough to be able to just walk up on the slab and get connection to the sensor. So you get the data for real-time temperature, and after that, just the equations are very, very simple. You just embed the calibration parameters that you have developed in the lab, and it will give you the real-time strengths. But this is an MPa, so I don't know how much is in PSI, but you get the real-time strength. So you can change the units, you can change the calibration, you can assign for each sensor a separate calibration on the app. And you will get in the list of all the sensors that you have, and you'll be able to very, very conveniently and intuitively connect to all these sensors and make decisions on the go on if you want to do the formwork stripping, if you want to stop heating the slabs, if you want to open traffic, especially in fast high-track projects. And you also have the profile of temperature and profile of strength. And again, as the previous presenter presented, you can easily share this. So the shareability using mobile apps is impressive. So you can email it right away, put it in Dropbox, and your coworkers can make a decision as well on what they're going to do next. So we took this one step further, actually, to develop a smart concrete. So essentially embedding the sensor, instead of putting it in the slab, putting it in the truck. So the sensors are pre-calibrated with the maturity curves, and they are placed in the truck, and the truck delivers a smart concrete to the job site. So the end users don't really have to do anything. To just simply download the app, connect to the sensor, and they can see the strengths when the concrete is placed in the job site. So this is making the whole practice very, very seamless. So, and it's essentially that because we have mobile technology that makes it possible. It wasn't possible before. So, so that's sort of the smart concrete that is also part of the smart technologies that are available nowadays. And it's very easy in the fixing station at the bashing plant when they want to send the truck off to the job site. They just put the sensor in it, and they assign the calibration on the sensor, so the end user doesn't know even what calibration that sensor has, just sees the real-time strength. And the other technology that I showed you earlier, like resistivity and other sort of permeability assessment technologies, can also be combined into in-situ measurement technologies. So, this is a small resistivity box. It measures the electrical resistivity of concrete as well as temperature. And you can place it in the CPOC sample, essentially plastic mold, and put it on the job site. And when you pour concrete, it has filled the concrete. So what it does is that it measures the change in the electrical resistivity of concrete from the freshest stage up to hardest stage and after that. And then the same concept, you walk up with your mobile phone, connect to the sensor, and download the resistivity information and temperature information. And there has been recent studies at NIST and by other researchers that show that the resistivity can be correlated to setting time, which is very, very ideal for finishers. They can decide when you want to do finishing based on that. And also permeability, water content. There was a research out of Berkeley by Paulo Montero correlating resistivity to water-cement ratio. So the technologies have been developed over the years, and nowadays it's possible to use mobile solutions to make them accessible and easy to use on a job site. So essentially, using this technology, you can get resistivity and temperature information, and can develop even equations and calibrations to estimate the strengths, again, based on other parameters. So all in all, you can have sensors, mobile-based applications to monitor properties of concrete from the freshest stage to pouring to finishing and while the structure is in service. And if one day we can resolve the battery issue, because these are limited battery powers, so we can run a couple months, maybe maximum 2 years, depending on the battery size. But if you want to do long-term pulse monitoring with these embedded sensors, we're not there yet. But the IT industry and the electronic industry is advancing so fast that I have no doubt that within a few years we'll be there. And so it's really phenomenal what's going on in that industry, and we have to bring all the solutions that are there and make them possible and applicable to practical solutions in the concrete sector. The last slide is just another solution that we have. It's not a sensor or a mobile-based technology for on-site measurement. It's just a mobile app for education. So I just wanted to put it up there that the collection of information that is out there is impressive. You have a lot of information published by bloggers, websites, magazines, online newspapers. To put them together in one location was one of the goals that we had developing the Concrete Hub mobile app. So essentially we had like 6 sections in the app, from videos, news, encyclopedia, tools, blogs, calculators, to have all of them in one place so that students, concrete professionals, everybody who's interested to get everything in one place, be able to download it and use it. So that's it for my presentation. If you have any questions, I'll be happy to answer.
The maturity, the thing I know is maturity life verification or the battery life. I mean, usually maturity you don't need to have it that long. So you're saying 3 months may be all you have to monitor it for, so you can put in a lesser battery, or the battery should last 2 years. What's the...
Yeah, the coin battery, a small coin battery, 3-volt coin battery, lasts for about 4 months on this technology.
So most of your products, what is the goal of the maturity for your target?
Only the first few weeks. Like, people are only concerned with the first few weeks. Even the
out to the 90 days and trying to make sure you tested with your brakes if you need to make cylinders as well, so your data is comparable.
Yeah. So the only application, or the most important application, is formwork removal,
Sure.
and they're only doing it within the first few days or week. So it's more than enough for them to have 4 months of battery. For another application, such as, say, if you want to monitor humidity of concrete, the same way. Humidity, we're talking about years. So you want to see when the concrete dries before applying flooring material. So for them, the battery can last for 2 years, sometimes 3 years. Any other questions?
What about compliance to local codes for testing results?
Yes, so the maturity is standardized, as I mentioned, by ASTM, and DOTs have, almost all of them have put it in their specifications. So it's ultimately up to the engineer, essentially, to say, okay, I'm confident enough to sign it, and then he or she has the tool or resource to leverage and say, okay, it is standardized, it is accepted by DOT, and I'm going to sign on the document that the strength is enough. Even if the engineer is conservative and doesn't want to do maturity and wants to say, okay, I'm going to do a break test, they can still leverage maturity to optimize the time of breaking samples. So instead of randomly sending samples of 1 day, 2 days, 3 days to the lab, they can monitor using the maturity technique and see, okay, after 13 hours and a half, the strength has reached 75% of the ultimate strength. Now send the sample to the lab and verify it, and then sign on the document.
It also serve as a go-ahead and continue meanwhile, even though we don't have
Yes, yeah. You can do it that way, yeah. Yes.
Have you used or planning to use this technology for mass concrete temperature monitoring?
Yes, so it is really advancing very quickly. So for mass concrete, you have to monitor, as you know, temperature at different depths from the surface, middle, bottom, even air. So with one temperature sensor at that cost, it's not really economical to embed like 4 sensors in the concrete to get that sort of gradient. So, but the technology is now there. We are actually prototyping that you can connect 4 to 7, sometimes 8 temperature sensors to one transmitter. So that way you can have one transmitter with so many different leads coming to different parts of the structure and makes it much, much cheaper and economical for field applications. Thank you very much.